Hi, I'm Rainer, and this is the first video for the Minds CSI Physics 1 series for the semester. So today we're going to talk a little bit about kinematics. So in this problem that we're given an acceleration function as a function of time, and the acceleration function is ae to the minus bt, where a and b are constants. We're told also a couple of initial conditions. We're told the velocity at time 0, and we're told the x position at time 0, and we're going to assume all of this is in one dimension, so we'll just call it x. And our goal is to find the position at time t2, and t2 is just a name of the time. So this is a little trickier than it sounds. We know that to get from acceleration to positions, we have to do some integrals. So let's go ahead and get started. We know, for instance, that if we want to write velocity as a function of time, and we have an acceleration, we can just take an integral to get there. And we know after that we can just take another integral to get to position. But we need to be really careful about how we do that. So I know that velocity of time is going to be equal to the definite integral, and I'll go ahead and put in a starting time of 0 and a final time of t of my acceleration function with respect to time plus my initial condition. And since it's a velocity equation, I need a velocity initial condition. So if I plug this in and I take this integral, I'll say this equals the integral of a times e to the minus bt. And I know that this integral is minus a over b e to the minus bt. And if that's confusing, you can check in with the calculus and it should make sense eventually. But we don't have time to go in detail about that right now. But remember, we've got to be really careful and take our bounds after we take this integral. We cannot leave it in this form. So we have to take this from 0 to t, and then add on, at v0, we have a condition of a speed v0. So I will put this on, and I can just tack it right on the end. So if I plug in these bounds, I plug in t for t, and I'm left with the same thing. But then I subtract off when I plug in 0. Notice when I plug in 0 for t, the exponential goes to 1, and I'm left with a minus a negative a over b, sorry. So I'm going to make that a plus a over b, plus v0. And then finally, I'm going to say, all right, x of t is just like this, but it's the integral of velocity. And so I'm going to take this full velocity function and I'm going to integrate it again. So I'll come over here and I'll say x of t equals integral v of t dt from 0 to t plus x naught, x of 0. And if I work that out and I take this integral, I'm going to get something like this. I'm going to get a over b squared e to the minus bt, that's the integral of this guy, plus a over bt, integral of this, plus v naught t, which is the integral of this. And then I'm going to evaluate that as well from 0. And now since I'm on the final step, I'm not going to plug in another t, I'm just going to go straight to the answer, which is t2. So plugging this in, I get a over b squared e to the minus b t2 plus a over b t2 plus v naught t2 minus, when I plug in my 0, notice this term still does not go away. And I'm left with this constant. But these two terms do go away plugging in 0. So I'm going to get a minus a over b squared. And up here, I didn't mention this a minute ago, but I really need to add on my initial condition like I did right here. And I know the x at time 0 is just a letter called d, so I'll just throw that onto the end. So that right there is the position at time t2 given this acceleration function.